Hello and welcome to our first of a two-part series covering oxygen and winemaking. Today we have Dr. Gavin Sachs, professor of food science at Cornell University, who's going to explain how oxygen reacts with juice and wine and how these reactions will drive wine style. Welcome, Dr. Sachs.
Great. Well, thank you, Johnny, for that kind introduction. And thank you to the organizers of the Oregon Wine Symposium for inviting me to speak this year on oxygen and winemaking. There's a lot that happens with oxygen in wine. So this talk is not going to be, out of necessity, fully comprehensive. Instead, I'm going to try to hit some highlights of what happens to wine and what I see as the three main stages. Pre-fermentation, during fermentation, or while the wine is still in contact with lees, and then finally post-fermentation once the wine is no longer in contact with lees. Fortunately, even if I don't get to a topic during this talk, we've got time for questions and answers. And so feel free to put things in the chat, and we can hopefully discuss them later. Okay, one piece of terminology I like to go over before proceeding into oxygen and wine. I'm going to use the term saturation or air saturation several times in this talk. Saturation is similar to solubility. Just like there's a limited amount of salt or sugar you can dissolve in water, there's also a limit on how much of a gas like oxygen you can dissolve as well. And if a wine or juice is air saturated, that means you're at the maximum concentration of oxygen at a given temperature, under or in the presence of air. So ordinarily, when you do things in the winery or at home, if you're trying to use one of these decanters, what you're changing is not the solubility of oxygen, rather you're changing the kinetics, how fast a wine or a juice is going to reach saturation, reach the point where you have as much oxygen dissolved as possible. Okay, so the concentration at which you reach saturation is temperature dependent. It's also dependent on ethanol content, but generally it's in the ballpark of 8 to 10 milligrams per liter, so not terribly soluble, with slightly higher levels of solubility as temperature decreases at colder temperatures. Okay, so we're going to start off with fresh must. Assuming that you've got no sulfur dioxide, the main route at which oxygen is consumed or reacts with must or juice components under these conditions is going to be enzymatic. That is enzymes either from the grape or hopefully not, but possibly enzymes from spoilage organisms like botrytis. And the reactions that take place in must or in juice that cause browning are the same ones that are going to cause browning if you slice open an apple, or you grate some potatoes, or you've got a banana that got bruised or left around and looks like it's ready to make banana bread, because I don't think I want to eat that one. The reactions responsible are promoted or catalyzed by enzymes. These go under the generic term of polyphenol oxidases, although they'll react with not just polyphenols, but simple phenols like this diphenyl captaric acid. And so these enzymes in the presence of oxygen will convert these phenols or diphenols into oxidized forms called quinones. And those quinones are pretty short-lived. They will only be formed following mechanical damage. That is, if you're crushing or pressing fruit or slicing into it, this allows those enzymes and these diphenols to mix, the reaction to proceed. It's quite rapid. And if you take hey, look at that, a prop. Take a dissolved oxygen meter and you take some grape juice, put it in a flask, shake, 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 shake. If you measure dissolved oxygen while that's happening, you'll start around saturation, 8 milligrams per liter, but within a minute or two, there'll be almost no measurable oxygen. Those enzymes are going to very rapidly consume oxygen so long as there's no SO2 present. Okay, another key aspect of these enzymes, there's no formation of hydrogen peroxide. And that's going to come up later when we talk about what happens during wine oxidation. In both grapes and in wine, there's formation of these unstable oxidized quinones, but there's no peroxide formation when it happens enzymatically as it does in grapes or juice or must. Okay, so it's called enzymatic browning because it results in browning. So we start off with a juice that contains these phenolic compounds, caphtoric acid, but also catechin, which is one of the building blocks of making tannins. These will undergo enzymatic oxidation to form these oxidized phenols called quinones. Those quinones then are highly reactive. They can react with other phenolics and form a range of diverse brown products. And so you start off with nice looking juice and it gets thoroughly oxidized, and now it's starting to look like dilute molasses. So you can slow down enzymatic browning. And most commonly in a winery, it involves the use of antioxidants, particularly free SO2. SO2 will react with the quinone, but even more importantly, it will deactivate enzymes like PPO. It's less effective on the PPOs that are found in molds, the lactases, but it still has some effect. Ascorbic acid, if you have kids and you cut open those apples and give them apple slices and you don't want them to brown, squeeze a little lemon juice on it. What this will do, the ascorbic acid can react with the quinone and reform the original diphenol, shut down this browning pathway. And then finally, glutathione, which is found in both grapes and in yeast, but in this case, we're mostly focusing on its source from grapes. This is a oligopeptide. That is, it's 3 amino acids stitched together, and they are also a good antioxidant. They have the ability to react with quinones, form a compound that's called GRP, or grape reaction product, which is possibly the strangest name of any compound I know of anything in wine. GRP generally is less reactive. It doesn't participate in further oxidation reactions. Okay, so that's one way. We can add various antioxidants which have different roles in slowing down the reactivity of polyphenol oxidase. You can also inactivate PPO through heating, or you can slow it down through cooling. Both of these processes will be used in wineries. If you do thermominification, especially on questionable grapes, that's one of the things that it's doing, is knocking out enzymatic activity from the grapes or from molds, in addition to killing off spoilage organisms. Cooling will slow down enzymatic activity. And then finally, treatments like fining agents like charcoal, bentonite can be used to bind to and remove some of the the browning products that are formed, as well as inactivate enzymes. Okay, so there's a number of terms that get thrown around to describe handling of musts or juices pre-fermentation. These do not have rigorous regulatory definitions in the same way that, I don't know, like a premium wine or a natural wine. Those aren't really tightly defined either, or reserved. The same way, oxidative, reductive, hyperreductive, some of these terms are going to be used by certain winemakers in a particular way and different than other winemakers. Generally, what I see is winemakers who talk about reductive versus oxidative. Reductive winemakers add SO2, and in oxidative winemaking, they don't add SO2. If it's hyperreductive, then not only will SO2 be added, but there will be an effort to minimize air contact pre-fermentation. This may include, for example, pressing under inert gas or otherwise trying to exclude air. While hyperoxidative, on the other extreme, means not only is SO2 not added, but air is intentionally added. And this will result in considerable amounts of browning of the must. And usually winemakers will then try to remove those brown products, say by flotation, flocculation, prior to fermentation. Okay, so what's interesting, if you look at literature and also some of my own experiences with trying some of the wines we've made here at Cornell, is you can start off with musts that are extraordinarily oxidized looking. Just, again, molasses-like. And then they go through fermentation and they start to lighten back up and eventually reform the color that looks pretty similar to what they looked like before fermentation. And if you look at papers and literature, when people do sensory or chemical analyses, the one effect that everyone seems to agree upon is that if you do hyperoxidation, intentionally expose a must to oxygen with no SO2, and then remove the brown products, say by flotation or filtration, you will decrease the browning potential of that eventual wine. That means once you're done with winemaking, if you allow SO2 to go low, then those wines that went through hyperoxidation are not going to appear as brown. Also, more oxygen, more potential for aerobic spoilage. That's kind of a trivial statement. Everything else is either really minor or contradictory and hard to reproduce. It doesn't mean that hyperoxidation or intentional oxidation of must isn't going to have any effect, but things like aroma, taste, and mouthfeel, occasionally there's reports of having effects. They tend to be pretty small when they're present. And so some speculation as to why. Keep in mind that fermentation is a strongly reducing environment, reducing being the opposite of oxidation, the opposite reaction. And we have, yes, these pre-fermentation oxidative reactions happening if we intentionally expose our wine, sorry, not our wine, our juice to air, but we're doing that for a relatively short amount of time, and then we've got a much longer, more intensive reductive period after that that can reverse or counteract some of those oxidized or oxidative changes. Okay, the other reason why pre-fermentation oxygen exposure might not have a major effect, especially on things like aroma compounds, is most aroma compounds found in a finished wine are not present in the juice or in the must. Rather, they exist in a precursor form or are produced de novo by the yeast or by lactic acid bacteria. So as an example of one of these precursor form compounds, we have 3-mercaptohexanol, or 3-MH among friends, which has an odor of grapefruit or citrus or passion fruit. This compound is most closely associated with Sauvignon Blanc wines, although it's also found in a number of other whites and rosés and occasionally even reds, but it's absent or nearly absent from grapes. Instead, this compound is formed from precursors that are present prior to fermentation and then released by yeast during fermentation. There's a number of pathways that have been identified for 3-MH precursor formation, but here's one of them that's been particularly well understood. So you take a neutral grape variety like Chardonnay or Pinot Grigio, and you crush them up. Typically, it doesn't smell like a finished Chardonnay or finished Pinot Grigio. Most often, at least around with the grapes that we have here in New York State, it smells like someone who's just mowing the lawn. It smells grassy or green. And this is due to the same compounds that are responsible for the smell of fresh cut grass. These are aldehydes formed following mechanical damage to the skins, starting from fatty acids in the grapes. Crush up those grapes, fatty acids get oxidized, they've released these cut grassy smelling aldehydes. Those compounds are highly reactive with anything that's an antioxidant. For example, glutathione. I already mentioned this compound. Again, it's a tripeptide, 3 amino acids. It has this SH group, this mercapto or thiol group, that's highly reactive with aldehydes. And if these two come into contact, which they will, if you crush the grapes and let them sit around for a while, they'll react and they will make this odorless precursor, which does not have a clever, cute name like grape reaction product. It's just called the glutathione 3-MH precursor. And this compound is odorless. And you can tell that because I spent time figuring out how to gray out the color. And that way, you know, because it has no color, it's got no odor. But then this compound, odorless, goes through fermentation and 3-MH gets released. And now you have a wine like a Sauvignon Blanc that smells like grapefruit or citrus or passion fruit. All starting from this precursor, which isn't present even in the intact grape. You have to crush the fruit, bring these new aldehydes in contact with glutathione. Now you have this glutathionated precursor. Okay, so I mentioned a couple compounds that are readily oxidized. Glutathione, readily oxidized. 3-MH, that grapefruit smell, very easily oxidized. So what happens if we introduce oxygen, or going the other way, prevent oxidation pre-fermentation? So there's been some work on this, looking at various precursor fractions and either oxygen exclusion or the use of antioxidants. one of the things that's surprising is hyperoxidation has a small effect, but not a huge effect. That is, you can intentionally oxidize a juice must, Sauvignon Blanc, and yeah, there's a small decrease eventually in wine thiols, but it's like 30%. It's not very much. So what's going on? Well, there's probably some loss of glutathione. But interestingly, if you go the other way, if you use a lot of antioxidants, you try to exclude air contact, it can actually also decrease these precursors. So what's going on? This is counterintuitive. You're trying to make these thiols, which are readily oxidized, but if you add lots and lots of an antioxidant, you actually make less. And probably what's going on is that too high levels of SO2 in particular may inhibit formation of those aldehydes once you crush the fruit, and you need those to make the precursors. So both extremes seem to actually cause a decrease in eventual thiol content. Too much oxygen, too little oxygen, or going the other perspective, too much antioxidant, too little antioxidant. All of this, though, is a small effect as compared to what happens if you harvest the fruit, you have some mechanical damage, and you just let the harvested fruit sit around prior to fermentation. If you mechanically harvest fruit, just let it sit around. Here they transport it, but you don't need to transport, you can just hold on to it. This allows time for these glutathione 3-MH precursors to form, and the resulting wine will also have more 3-MH, more intense Sauvignon Blanc aromas. This work originally was came about because people noted that when you had mechanically harvested Sauvignon Blanc, you formed more thiol aromas, Sauvignon Blanc type aromas in the resulting wines. So yeah, oxygen has a small effect. Yeah, antioxidants have a small effect, but I always focus on what are the big levers. And here it's not oxygen. Here the big lever is, do you allow time for your precursors to react to make precursors? Okay, so longer harvesting time, more time for precursors to form. This seems to be the big lever as opposed to oxygen or oxygen exclusion. And it's these types of lack of changes to make me say, yes, there's an effect of pre-fermentation oxygen exposure, but it's small as compared to some of the other things that you can do in the winery. Okay, so during fermentation, oxygen consumption continues to be relatively rapid. You can take a fermenting must, saturate it with oxygen, and you will see that oxygen go down to near undetectable within a couple minutes. And that's in part due to CO2 being formed and driving out oxygen, sparging it out, but it's also because the yeast will utilize oxygen enzymatically. And they have a number of uses for oxygen. One of the big ones is unsaturated fatty acid production. Okay, so here's a yeast cell. It's a picture of one. And the yeast cell has a wall on the outside, and inside that cell wall is a cell membrane. Just like our cells. Our cells have membranes too. And those membranes are composed of phospholipids. And those phospholipids have fatty acids. The yeast are going to try to modify these fatty acids and thus their cell membrane in response to their environment. They have lots of choices for fatty acids. And when they experience colder temperatures, they prefer to increase the concentration of unsaturated fatty acids. That should remind you of like nutritional science, right? Unsaturated, saturated fatty acids. So you know about saturated fatty acids. Something like butter has higher concentrations of saturated fatty acids. Saturated fatty acids have higher melting points. They're more likely to be solids at room temperature, as opposed to something like olive oil, which is going to be a liquid at room temperature. Unsaturated fatty acids have lower melting points. If you're the yeast and you want to have the same, what's referred to as fluidity or flexibility in your cell membrane, then it's beneficial to convert some of those saturated fatty acids into unsaturated fatty acids to increase that fluidity and maintain a cell membrane that's appropriate for a cool fermentation temperature. But there's a problem. Look at this step. It's enzymatic and it involves oxygen. So if you're having a fermentation being done in a low oxygen environment, this is eventually what often ends up slowing down fermentations and slowing down cell growth by yeast. So assuming everything else you need is there. You've got nitrogen, you have other nutrients, other vitamins. Very often it's oxygen that ends up being the limiting nutrient. And so there's several studies that have looked at this effect. You can take a fermentation, you can add in oxygen as a nutrient, spike it in. You'll be doing this in a winery. If you're doing any kind of transfer operation, you do rack and return, you do a punch down, you're almost certainly going to be introducing oxygen to some extent. And this is going to stimulate yeast growth. So under low oxygen conditions, yeast find it challenging to produce unsaturated fatty acids and sterols, which also help them modify cell membrane composition. This is going to limit yeast growth and fermentation rate. This is particularly acute, this need for oxygen, when you have cool fermentations, because the yeast want to produce more unsaturated fatty acids. When you have closed top fermenters, exclude oxygen, and when you've got very low insoluble solids, that is more clarified mousse. What I've just described is the way we typically make fruit-forward white wines. Cool fermenters, closed top, well-clarified mousse. Those conditions are also some of the most challenging for the yeast because they don't have as oxygen available as a nutrient, but they also have the highest demand for that oxygen to make more unsaturated fatty acids. So it's pretty common then when you've got a fermentation that's going a little slow for people to suggest, well, don't just add nitrogen or other nutrients, but also introduce air. In fact, it's hard if you're doing an addition not to add air as you're doing it, which can confound the number of experiments that try adding things. Well, in the process, you're adding air. Maybe that's what ended up having the effect on the fermentation. Okay. So there are other effects of adding oxygen, maybe desirable, maybe in the case of this first point, undesirable. There's a lot of other microorganisms that will also happily increase their growth rates in the presence of oxygen, not just the yeast strains that you're using. And many of these other yeast strains, or in the case of something like Acetobacter, are going to produce higher levels of DA under aerated conditions. Saccharomyces cerevisiae is nice because in the presence of oxygen, they don't increase DA or acetic acid ethyl acetate production. Oxygen is going to affect amino acid and fatty acid production. These biochemical pathways are linked to formation of a number of flavor compounds. For example, if oxygen goes up, acetate ester production goes down. Acetate ester, that's the banana, cherry, Beaujolais, Nouveau type aroma. This is part of the reason why Beaujolais Nouveau is made the way that it is. It's not just a carbonic maceration, it's that you press early and ferment like a white. Decreased concentrations of other compounds, ethyl esters with kind of a generic fruit salad type aroma, increased concentrations of fusel alcohols or higher alcohols, increased concentrations of branched chain fatty acids, and eventually their ethyl esters, which smell more like the fruit that you get from a red wine. So finally, you also have some effects on biomass. This part in here in the middle, this is kind of a recipe either for or against making a typical fruit-forward white. If you're trying to make like a generically fruity white or rosé, it's very common to try to exclude oxygen, and the reasons are you want often to increase production of these straight chain ethyl esters, acetate esters, and decrease production of things like higher alcohols that will mask that fruitiness. This is less of a problem for red wine production. Okay. So finally, this takes us to what happens at the end of fermentation, post-fermentation. And post-fermentation after filtration or several rackings and SO2, because we no longer want to have lees activity. If you're on lees, if lees are present, lees can continue to consume oxygen at a slower rate than an actively fermenting wine, but sufficiently so that that would be the major route by which oxygen is consumed, as opposed to through these non-enzymatic pathways that we're about to discuss. Key thing here, look at the effect on the oxygen consumption rate. Fresh must, actively fermenting wine, we're consuming oxygen at a rate of a few milligrams per liter per minute. And post-fermentation, get rid of yeast lees, now we're at 1 milligram per liter per hour or less. So non-enzymatic oxidation goes much more slowly. This is part of the reason why we don't even think about it during these earlier stages of grape and juice handling or during fermentation. Those other pathways are 100-fold or greater faster. They're going to consume the oxygen. Okay, so main effects of oxygen on a finished wine, something I'm not going to go into much detail about, microbial growth. Due to the presence of oxygen, there's certain things that are functional aerobes like acetobacter, film yeast that are going to need oxygen. But also when you've got oxygen present, it will consume SO2, and then this can then allow for the growth of other organisms like lactic acid bacteria or Brettanomyces. This can result then in off flavor formation, haze formation. If you make VA, now maybe you have a regulatory issue. What I'm going to focus more on are the chemical changes, what we refer to often just as oxidation. And that's the next slide. And for that matter, the slides after that too. Whoops. Okay, so we've got two pathways that are well established to happen if we take a wine that has little or no SO2 and we expose it to oxygen. One I refer to as the iron phenolic pathway because it involves oxygen and iron and a phenol. Again, another diphenol, just like we saw when we were talking about what happens to must as it oxidizes. The difference here is instead of having an enzymatic catalyst, PPO, now we've got iron as a catalyst. Okay, so this reaction proceeds. It'll form a oxidized diphenol, a quinone, just like when we oxidize must pre-fermentation. But the big difference is that we also make hydrogen peroxide. These two compounds, highly reactive. They can result in loss of sulfidrals. So this can be bad if you're losing 3-MH, that compound responsible for the citrus or passion fruit, tropical grapefruit aromas of some white wines and rosés. It could also perhaps be a good thing. It can result in loss of these rotten egg and cabbagey smelling thiols, which often are called, well, methylmercaptan is often just called mercaptan, but they're chemically synonymous. So that could be good, that could be bad. Hydrogen peroxide will react with iron to generate hydroxyl free radicals, which can undergo something called a Fenton reaction. And then those hydroxyl free radicals can react near indiscriminately with wine components to generate compounds like aldehydes, including acetaldehyde, by oxidation of ethanol. These are the compounds that result in the oxidized smell of wine. We've got compounds like acetaldehyde that smell like bruised apples, sherry, and walnuts. Methionals, another one, smells like baked potatoes and soy sauce. We'll also produce browning products. And so hydrogen peroxide's effects are largely to generate the main effects we associate with oxidized wines. So that's the main pathway. There's a minor pathway, at least quantitatively minor. It's not the main, it's minor insofar as there's not a whole lot of oxygen that seems to go through this pathway, but it can still have a major effect. It involves trace transition metals, copper, iron, reacting with oxygen, and sulfidrals. Again, there can be both good forms, 3-MH, 3-MHA, it's compounds that give that tropical aroma. It could be things you wouldn't mind seeing going away, like H2S, rotten egg, or methylmercaptan. And the resulting compounds are going to be odorless. Okay, so chemical oxidation, I was focusing on the bad parts. It's not necessarily bad. There is times when people will intentionally oxidize their wine. I did mention one of it's an opportunity then to oxidize hydrogen sulfide. Although there are other strategies that may be preferable if you don't want that H2S to reappear. Another reason people will intentionally oxidize their wines is micro-ox. In a micro-ox, the idea is that you will allow the anthocyanins in your wine to react with sometimes, but not always, tannins in the wine, and to react with aldehydes that can be formed as a result of wine oxidation. And this will result in compounds that are referred to as wine pigments. Sometimes they're also referred to as polymeric pigments, although they don't necessarily need to have tannin polymers in them. So I think wine pigment is more descriptive. They're less bleachable by SO2. They're less prone to hydrolysis, so they're more stable in a wine environment. They're also the major contributors to the color of aged wines. And there's several experiments showing that indeed, if you do micro-ox at appropriate levels, how appropriate here is roughly at the same concentrations as an air saturation, ballpark of 6 to 9 milliliters per liter. That's about milligrams per liter per month. This will increase, in this case, color intensity, and also increase wine pigment and slightly decrease astringency. Note that these are modest effects, but they're still perceivable. So what is this, a 10% or so increase in color intensity? Okay, so there can be a role for intentional oxidation to increase color stability and to affect perceived astringency and mouthfeel. So most wines, however, are not exposed to oxygen in the absence of SO2. Most wines do have SO2 during storage. And a quick review, free SO2. Free SO2 has two components, molecular SO2, the neutral form, which is SO2 as SO2, and bisulfite, which is HSO3 minus. At wine pH, bisulfite is the major contributor to free SO2. Usually it's 95% or more of the free SO2. Molecular is a small part, but it's important because molecular SO2 is also the antimicrobial component of free SO2. Typically, people target in the ballpark of 0.5 to 1 milligram per liter of molecular SO2. Higher values are more common with wines that are at risk for re-fermentation, like sweet wines. Lower values might be more likely to be used for a dry red, where there's less worry about yeast spoilage and more worry about lactic spoilage. The other role for SO2, or free SO2, is as an antioxidant. Bisulfite, the main component of free SO2, can bind to or prevent the reaction of oxygen, or I should make more properly, it binds to or consumes reaction products from oxidation. It does not react directly with oxygen. So at below about 10 milligrams per liter, free SO2, oxidized aromas or other signs of oxidation like browning start to become evident. And most winemakers will target free SO2 concentrations in the ballpark of 30 milligrams per liter at packaging or during storage. And of all the functions of SO2, this is the hardest one to replace. There are other options, for example, to prevent spoilage. DMDC, pretty impressive as a broad spectrum antimicrobial. But replacing this function of free SO2, especially at very low levels, and not having wine smell oxidized can be pretty challenging to do, and we'll talk about why. Okay, finally, bound forms. If you have SO2 added to a wine, a portion will stay free, but a portion will also form covalent bonds, strong chemical bonds, with what are referred to as binders, other components in wine that will make these forms called bound SO2. And bound SO2 has less, sometimes even negligible, antimicrobial activity and antioxidant activity. Bound SO2 and free SO2 are in equilibrium. What that means then is as free SO2 is consumed during wine oxidation, bound SO2 will re-equilibrate such that it'll partially replenish the free SO2 pool. It acts like a reservoir such that free SO2 will decrease more slowly than total SO2 will decrease, because there's always a portion of free SO2 getting replaced by the bound portion. Okay, there's a long list of SO2 binders that have been identified. Here is a partial list of some important ones. The strongest SO2 binder found in wine is acetaldehyde, which is the oxidation product of ethanol. Again, it has this bruised apple, sherry, walnut type aroma. If acetaldehyde is present and you start adding SO2, you will not have any measurable free SO2 until you have nearly completely bound up that acetaldehyde. Other compounds in wine that are also binders are weaker binders. For example, methionine, present at much lower concentrations than acetaldehyde, but a very potent odorant, and it contributes to the oxidized smell of oxidized wines. Anthocyanins, which have a reddish purple color, those key pigments. glucose, high concentrations in sweet wines. All of these can bind SO2 to varying degrees, which will, for example, in the case of methionine and acetaldehyde, result in compounds that are no longer volatile. And this is, again, a reason to have SO2 present. It prevents these malodorous aldehydic compounds from being volatile, and thus from being odorous. And unless you are making a port or a sherry type wine where those compounds are expected to be present, that's probably going to be desirable for your wine. Okay, so this big slide again. 2 pathways, major and minor, potential changes, both good and bad, to a wine. The role of SO2 is not to react with oxygen. Rather, the role of SO2 is to consume those oxidation products. SO2 can react with the quinone. It can react with the hydrogen peroxide. It can react with oxidized copper and oxidized iron, preventing it from reacting with sulfhydryls. Or once you have the reaction take place, it can react with those downstream products and at least partially reform some of the original products. So again, the role is not direct consumption. It is a reducing agent. It does the opposite of oxidation. It will chemically reduce those oxidized intermediates, and that's what prevents oxidized changes or chemical oxidation from happening to your wine. And if this is especially if it's the iron phenolic pathway, if that's the only pathway happening, we expect to see 4 milligrams per liter of SO2 total get consumed for every 1 milligram per liter of oxygen. Okay, so to wrap up, I'm going to show some new research that we've been working on, which is, if you're paying attention, you should have noticed that there was 2 ways that a wine could start smelling oxidized as it is exposed to oxygen and consumes SO2. The way that we usually talk about it is that oxidation results in production of new aldehydes. So we have this iron phenolic pathway. It makes peroxide. Peroxide goes through what's called a Fenton reaction, which generates free radicals. And then we produce acetaldehyde from the oxidation of ethanol. So that right now, at least that's the way I was teaching my students until a couple of years ago, that's the way we're thinking wines start to smell oxidized. They start off with low aldehydes, get exposed to oxygen, SO2 eventually gets low enough where we can have this de novo production of aldehydes. But there's another pathway, which is what if all of our aldehydes were already there? They were just bound up. In that case, the way that a wine is smelling oxidized is not because we're making new aldehydes, rather we're consuming free SO2, and that's releasing bound aldehydes from bound SO2 forms. So instead of forming new acetaldehyde from oxidation of alcohols, rather we're releasing previously formed oxidation products. So I had the opportunity to collaborate with Pat Howe, who at the time was working for a company that was doing a large trial of bag-in-box packaging, which is wonderful as an experiment because bag-in-box allows for relatively rapid exposure of wine to oxygen. And these trials were done with different packages, different temperatures, and free and total SO2 were measured out to 400 days. The rate of total SO2 loss was relatively fast as compared to glass packaged wines, but it's still slow enough that any oxygen that made it into the package would be consumed faster than oxygen could get in. So when we measure dissolved oxygen in these wines, dissolved oxygen is almost always near zero and undetectable. So oxygen is getting in, but it's being consumed by the wine, but it's also happening relatively fast. So we can see over the course of a year, all of the SO2 getting consumed. So what would happen if we had wines where we're making new aldehydes? So this is not real data, this is hypothetical data. What I expect to see is something like this. You start with a wine, it starts with high free SO2, high total SO2, and both get consumed, and eventually they both plateau. Free SO2 plateaus because you're at zero. Total SO2 should plateau because eventually you start making new aldehydes, and all that's left is going to be these strongly bound aldehyde SO2 complexes, especially acetaldehyde bound SO2. So if what's happening is new aldehyde formation, Fenton reaction becomes important at low free SO2. As free SO2 approaches zero, total SO2 should plateau because we're making new binders. That's not what we see. What we see is that the rate of total SO2 is basically constant throughout the course of oxidation. Even once free SO2 goes to zero, total SO2 continues to decrease at this steady linear rate. Even that strongly bound acetaldehyde, what people sometimes call irreversibly bound, it's not irreversibly bound. This isn't a good wine, by the way. You're starting to release lots of acetaldehyde, but even that SO2 bound to acetaldehyde will eventually be consumed during oxidation. And we see this with a Chardonnay. We see the same results with Merlot and with the Cabernet Sauvignon, regardless of packaging and oxidation rate, regardless of temperature. What we think this means is that the most important source of aldehydes when you oxidize a wine, it's not making new aldehydes. These are aldehydes that are getting released from bound forms. And these bound forms were in your wine since the end of fermentation. They've been there since the beginning, when you first added SO2 at the end of a fermentation. So why do you care? Why is this more than just academic? Well, one of the questions is that one of the possibilities is that if these are bound forms that we can get rid of at the end of fermentation, can we get rid of them before sulfiting? Can we do that, for example, with lees contact in the way that brewers do with lagering beer? Can we then have wines that smell fresh even at low SO2? Another is, well, during microoxygenation, we thought we were making acetaldehyde de novo. Is it that we're releasing it from bound forms? Perhaps that's what's going on instead. And could this help explain some of the variability that we're seeing during microox? Okay, so as a quick review, the pre-fermentation versus during fermentation versus post-fermentation, all of these are going to lead to different outcomes. And I appreciate your time, and hopefully we'll have some time for some questions. Thanks.
Thank you, Dr. Sachs. That was very informative. And I think that we have some follow-up questions with that. So you talked about reduction in wine, and I know that that's very common here in Oregon. And some people revert to using copper sulfate as a way to mitigate that. Could you reflect maybe more on how copper is used and what it's doing in the wine?
Yeah, that's good. And that ties in well with oxygen, because the two standard approaches that we have for addressing sulfurous malodors, so hydrogen sulfide, methyl mercaptan, related compounds, involve either the addition of copper as copper sulfate or the addition of oxygen to intentionally try to oxidize the wine. And I discussed the pathways by which those malodorous sulfur compounds will be lost. So there is still debate about which is the more appropriate tool to use. And in both cases, one of the main concerns is that even once you address the issue of H2S or methyl mercaptan, there's a chance for reforming those compounds during storage. So I'm not sure if this is what you're referring to. I know here in the Finger Lakes, we certainly have examples of winemakers who have a wine that's a little stinky. They clean it up either by aeration or by copper fining, and then they put it in the bottle, and then 3 months, 6 months later, the wine's stinking again the way it did before. So in the case of copper, one of the myths associated with copper use is that you add copper, smell goes away, and you've made copper sulfide from H2S, and all just precipitated out. This is not what happens when you add copper to a wine. It's what happens if you add it to pure water containing H2S. If you add it to a wine, copper sulfides will form, but they'll stay in solution. They'll make nanoscale particles that cannot be filtered out. They will not settle out easily. And the estimate is something like 80% or more of copper that gets added to a wine stays in the wine, even following standard membrane filtration. There's some strategies that have been proposed to remove this copper. For example, there are some specialized pads, filtration pads that are designed to remove copper. Lees fining seems like it can help remove copper. But if you don't, those copper sulfides during long-term wine storage can then react with bisulfite, free SO2, and reform H2S or reform methyl mercaptan. These seem to be one of the main sources of reduced off aromas in a stored wine. So my main recommendation is if you're going to use copper, don't assume it all precipitated out. measure your copper. And if you still have high, not from a regulatory standpoint, 0.5, you should be well below 0.5. 0.1, 0.2 would be a reasonable target to achieve using some approach to remove that copper if you're going to use it. The other suggestion I have for copper is the earlier you add that copper, the less likely it is to hang around and less likely it is to have copper sulfides around to be released during storage. So if you add copper early, it will bind to some of the other poorly soluble compounds in wine and usually can be removed by racking.
All right, wonderful. I had another question for you that was towards the beginning of your presentation, and that was about some of the precursors that form the 3MH. Are those precursors found in all grape varietals, or is it specific to maybe the more aromatic types like Sauvignon Blanc?
Yeah, those precursors. So they're not found in the intact grapes, but anytime someone has tried to measure those precursors in all grape varieties, in crushed fruit, you find them. And if you go looking for them in finished wine, so long as the wine was not made post-fermentation in a more oxidized style, like a lot of reds would be, you will find those thiols, 3MH related compounds. So you can find them, of course, in Sauvignon Blanc, but they're present everywhere people look. You can find them in Cabernet Sauvignon, or rosés made from it. You can find them in Pinot Grigio, you can find them in Riesling. What sets Sauvignon Blanc apart is, for reasons that aren't all that well understood, it tends to produce wines that have higher concentrations of 3MH and some related thiols.
Okay. I've noticed this trend in Oregon as far as crushing and having maybe more skin contact with Chardonnay. Can you maybe touch on how that could impact the aromatics of the Chardonnay?
Yeah, that's interesting. As I mentioned during the talk, there's multiple things happening if you're going to crush and wait prior to fermentation. I'm assuming this is not with a lot of SO2 present. Number one is, yes, oxygen itself can have an effect. There can be loss of glutathione that may decrease some of those precursors of things like 3MH. But simply allowing that must to sit around and wait allows for formation of more of these precursors, especially if it's not highly processed, if not strongly crushed, if it's partially damaged. So more important than the role of oxygen there is the role of crushing or damaging, slightly crushing, and then waiting. And that allows more of these precursors of thiols to form, which means if I had to make a guess, I would assume that that Chardonnay where you did that is more likely to smell more strongly tropical than one where you did pressing on whole berries, whole clusters, and didn't allow time for those precursors to form.
Sure. And I mean, just throwing darts out there, is there a recommended amount of time that you would see that increase, or is there a kind of a range, or is it just kind of what you get is what you get?
Yeah, the experiments that have been done so far have been trying to mimic the standard amount of time that someone might allow for grapes to sit around without starting to ferment spontaneously. So usually people are doing these experiments over a day or 2 or 3. They're not going 2 weeks because once you go out to those lengths of time, chances are you've got some fermentation starting, even if you haven't inoculated. So it looks like these precursors will form pretty rapidly, and you're going to see noticeable, even order of magnitude changes in both thiol precursor formation and eventual wine thiols within a couple of days, and probably even less. It should happen faster, the warmer the temperature. The scary thing there is warmer temperatures also means greater chance of spoilage. This is not something I would try on any fruit that was not sound.
Okay. And are those precursors pretty stable until they do go through the process to where they're cleaved essentially?
Yeah, they are. The precursors of those volatile thiols are very stable. In fact, they can't be released even in the wine under non-enzymatic conditions. That's why you need the yeast or other microorganisms to facilitate their release. So they're going to be stable into fermentation. The problem is if they don't get released during fermentation, then they're not going to get released into the wine. Your next chance after that is when you drink the wine, you actually can get some released in your mouth and give you an aftertaste of those thiols in your mouth. But people often want to be able to smell it in the nose, not just retronasally.
Sure. I have one final question for you. At the beginning of your presentation, you showed us a DO meter. Can you maybe elaborate on when and why it's important to use a DO meter?
Yeah, so dissolved oxygen meters. If I only had one time to use this DO meter or any other DO meter, it would be at packaging. If you're bottling your wine, seal it up, that's your last chance. If you allow a lot of oxygen in then, that oxygen is eventually going to be consumed. Yes, we talked about things like metal catalysts, but regardless of how much iron you have, copper you have, eventually that oxygen is going to be consumed. And if you pick up a lot of oxygen, you're going to be losing SO2, and eventually you might have some undesirable changes happening to your wine. So if there's only one time, it would be DO meter, or someone was using a DO meter to evaluate how much oxygen is getting picked up, not just in the wine itself, but also in the headspace, to evaluate how much total package oxygen you're picking up, and therefore figuring out if you need to make adjustments to your bottling line or add a little more SO2 to compensate for those problems that you have. Working back from there, if I'm allowed to use a DO meter more frequently, at the other extreme, prior to the end of fermentation and getting the wine off lees, I don't see a lot of value with using a DO meter. And the reason is, if it's freshly crushed grapes, if it's lees, if it's for active fermentation, those systems are pretty rapidly consuming oxygen. And what you can do, I mean, it's kind of fun to watch the values drop quickly, but I don't know what you can learn from that. The time when DO measurements start to become useful are once you rack off or filter off or get the wine off the lees. Now you no longer have enzymatic oxidation being dominant. Now you have non-enzymatic chemical oxidation being the dominant route for oxygen to be consumed. And that can cause undesirable changes in flavor, or maybe desirable changes in flavor. But these are, for you to understand this, you need to know how much oxygen is getting into your wine. It can be a way to evaluate the integrity of your tanks. It can be a way to evaluate the quality of your transfer processes. You can now understand where your wine is picking up oxygen, how much, and then do something to address it. But working backwards, basically, the closer you are to packaging, often the more interested I am in making a DO measurement. And if you still have lees around, I'm not too interested in that number, other than strictly as an academic, as a research question.
Okay, thank you so much, Dr. Sachs. I think we can all agree that this was very informative and things to take to mind. So I hope that you join us for our next session, where we'll be looking at cellar techniques for oxygen management.